Hello, today's lesson we're going to talk about dynamics or the study of forces. The topics that we're going to cover today are Newton's three laws, the different types of forces, free body diagrams, which are an analytical tool that we will use to study forces and the resulting acceleration, and how to apply those free body diagrams to solve problems involving dynamics. First off, Newton's first law is the law of inertia. Inertia is the property of an object similar to mass, and for our purposes we can equate it as identical to mass, but inertia is the property of an object that resists acceleration. So the more massive an object is, the more force is going to be needed to accelerate it at the same rate. Okay, but Newton's first law basically says an object at rest will stay at rest, and an object in motion will stay in motion at a constant speed and in a straight line. We should be able to recognize that now as constant velocity. Okay, and the last part of this is very important. Okay, the last part of this statement says unless a net force acts on it. Okay, if there is a net force, the object will not stay at rest and it will not stay in motion at a constant speed and in a straight line. Okay, so this is going to be identical to what we're going to see in the second law. Okay, and it is important to remember the laws in their numerical order. Okay, so the first law is the law of inertia. Okay, Newton's second law states that the acceleration of an object is proportional to the net force acting on the object. So the more force, the more acceleration. Okay, and it's going to be inversely proportional to the mass or the inertia of the object. In formula form, we'll have the acceleration vector is equal to the net force. Okay, so we add all the individual forces up divided by the mass of the object. We may have seen this previously as F equals ma, but we're going to look at it this year as acceleration vector is equal to the net force vector divided by mass. The reason we're going to look at it this way is because the acceleration is the result of the forces, not the other way around, but the forces cause the acceleration. Okay. It's also important to not confuse the net force, F net, or the sum of the individual forces, with an individual force. Frequently I see students applying an individual force and trying to calculate acceleration based off a single force. Okay, that's not the appropriate way to do it. You have to add all the forces up, either graphically, as we'll see in a little bit, or also as algebraically. Okay, Newton's first law is equivalent to his second law when the net force is zero. Okay, if the net force is the zero vector, or basically the net force cancels everything out, okay, then my acceleration will be zero and therefore I'll have no change in velocity, either magnitude or direction. Okay, Newton's third law is important. It can be confusing at times, but we'll see a method that we'll use to try and make it a little bit simpler. But Newton's third law says that for every force there exists a force equal in magnitude but opposite in direction. If you push against the wall pushes back against you. If the wall did not push back against you, you would end up going through the wall. Okay, generally this is known as the action-reaction law, or as I like to call it, the equal but opposite law. The action-reaction word is a little bit confusing because reaction implies it happens one after the other. But the two forces exist simultaneously. If I don't push against the wall doesn't push against me until I start to push against it. Okay, just to summarize, okay, Newton's three laws. All forces will require two objects. An object providing the force and an object receiving the force. Okay, a source and an receiving object. Okay, forces that act at a distance like gravity or the electric field that we'll see later on, Okay, even in those situations, there are two objects involved. In the case of gravity, it's the mass of the Earth. Okay, so the Earth is acting as on the object. Okay, and we're going to use a source object format for labeling our forces. Okay, and the way that looks is that the force of object 1 comma object 2, or the force of object 1 on object 2. There are several reasons for labeling our forces that descriptively. The first reason is listed on the bottom, in that the Newton's third law pair becomes very obvious when you use that format, because all you need to do is switch the two object nouns, okay? So instead of saying force of object 1 on object 2, you can find the Newton's third law pair by switching those two and saying the force of object 2 on object 1. It will have the same magnitude but different direction, okay? And the different direction is 180 degrees, or the vector flipped 180 degrees. Okay, the different types of forces that we're going to encounter in this course are listed here. The first one that we're going to do, and every object with mass that is significant has a force of gravity. Okay, and we'll label it as the force of the Earth on the object. In shorthand form, and you'll see in the textbook occasionally, F sub g or W, because it's also equivalent to the object's weight. Or sometimes you'll see it also listed as mg, which is the magnitude, the mass of the object, times g, that 9.8 that we've been working on. Okay, the direction of gravity, we've always talked about it as being directly down, and that will always be the case until we move to planetary distances. Okay, the magnitude is simply going to equal mg, and like I said previously, this is known as the object's weight. Okay, so a 10 kilogram object will have a weight of 98 newtons. Okay, the second force we'll look at is tension force. This is the force that corresponds to strings, ropes, and chains. Okay, the direction on this one is along the rope. Okay, sometimes we'll abbreviate it as F sub T, or simply capital T. In long form, it's the force of the rope on the object, or if there are multiple ropes, force of rope 1, rope 2, okay, etc. There is no formula for this force, okay? This is a reactive force. So the only way we can calculate this, if it's not given, is by looking at the other forces and setting that equal to the acceleration of the system. Okay, the next one is spring force, the force of the spring along the object. Okay, in this case, the direction is parallel to the spring. It may be towards the spring, or in some cases away from the spring if you are compressing it. Okay, the magnitude in this case, or the strength of the force, is equal to K times how much that spring is moved. Okay, K delta X. We're actually not going to talk about springs in this unit, but I wanted to introduce it here because we will be using it in a later unit. Okay, the next one is applied force. We'll see this frequently. It's the force of an outside agent. Okay, we don't know what that agent is, so we're really not going to look too often at the third law pair to this force, but this is the force applied on the object. Okay, if an outside agent is given, force of the hand on the object, force of me on the object, okay, the direction will usually be given, or it'll have to be solved for. Okay, a major force that's often overlooked is the surface normal force. Okay, this is the force of the surface that is perpendicular to the surface. If I'm standing on the floor is pushing me up to keep me from sinking down through the floor. Okay, so this is the force, that surface normal force. Its direction is simply perpendicular to the surface. We'll use an abbreviation of F sub n, or in long form, it's force of surface perpendicular, comma, object. Since there's a perpendicular force, there is frequently also a parallel force, and that parallel force is friction. In this case, the direction is parallel to the surface, and it will be opposite the direction of motion. For instance, if you have kinetic friction or air resistance. Friction is actually more complicated, and we'll look at that and expand on this a little bit later in this unit. Okay, we'll also encounter other forces later on, and we'll talk about those at that point, in particular the electric force and the magnetic forces. Okay, free body diagrams is the primary tool that we will be using. Okay, they help us to analyze the multitude of forces on an object. What we do is we model the object as a single point located at the object's center of mass. And then we'll draw all the forces, identify all the forces, and draw them approximately to scale starting from that center of mass dot. Okay. And if you know the direction of acceleration or can intuit the direction of acceleration, it's good to draw that off to the side. The reason for that is because the net force, or the sum of all those forces, should be in the same direction, or the resultant of that should be in the same direction as acceleration. Okay, so let's see what that looks like. Here's an example. I have a 12-kilogram wagon is being pulled by a little boy pulling on the handle with a force of 42 newtons. Okay, and the handle makes an angle of 30 degrees to the horizontal. Okay, so let's draw the free body diagram associated with this. Okay, first off, we draw a dot roughly in the center of mass. If you don't know where that is, just put it in the center of the object. Okay, we'll see later on that it doesn't even have to be at the center of the object. We'll move it off to the side so it doesn't interfere with our picture. But right now, let's just add the force of gravity on there. Okay, we know the wagon has a mass. It's an object. We've lifted them. They're heavy. Okay, in this case, the force of the earth on the sled, straight downwards as I mentioned, drawn to scale, okay, and this is going to be equivalent to the mass of the wagon, 12, times g of 9.8. Or if we use 10, okay, the force of the earth on the sled, or the weight of the sled, will be 120 newtons. Okay, the surface is also pushing up on the sled. Okay, in this case, it's not going to be pushing up quite as much as the weight of the object. We'll see why in a little bit. Okay, so it should be a little bit shorter. If you can't figure that out, it's okay. We're just looking primarily at the direction. The scale vector may come later. Okay, in this case, the surface is flat and the sled's on top of it, and so perpendicular to that would be straight upwards. Okay, then we have a force applied as described. Okay, it's at an angle and roughly 30 degrees, and we'll label that with its magnitude, which was given as 42 newtons. Okay, so that's our free body diagram. There's no need to actually, oh, I forgot, okay, there should be an acceleration, which we'll figure out later on, and but the acceleration is to the right in this case, and I just label it there. We don't know its magnitude yet, so we're not going to put a value there. Okay, and we can offset this. There's no need to actually keep it on there. As we get more practice, it'll be a lot easier to just draw it off to the side so it doesn't get cluttered with the picture. Okay. In this case, we had a force at an angle. The applied force was at 30 degrees. And just like we did with projectiles and vectors before that, okay, we're going to need to resolve that into its x and y components, because we're going to need to treat the x components and the y components separately, because we can then add up all the x components and add up all the y components to get my acceleration vector. Okay, so the next step, it's the same problem, okay, but now we're going to resolve the various forces. So here's my free body diagram from before. Okay, the force applied is at 30 degrees, and we have to use a little trig, so remember our SOHCAHTOA. There that is, okay, and the y component now simply becomes the force applied, or that 42 newtons, times the sine of that angle theta. Okay, and then we have the x component. Okay, the force applied x becomes the hypotenuse, or that 42 newtons, times the cosine of that angle theta. Okay, and there it is, and we can therefore replace the force applied with the x and the y components. Okay, and that way we can work simply in the x axis and simply in the y-axis without having to use the complex x hat, y hat format. Okay, now applying Newton's second law, or A is equal to F net divided by mass. Okay, so Newton's second law tells us that the acceleration of the object is equivalent to the resultant of all the forces added together divided by the mass of the object. In general, we will treat the x and y forces separately. So I can add up all the x forces to find what my acceleration in the x is, and add up all my y forces to find out what my acceleration in the y is. And then I could put my full acceleration vector together as ax, x hat, plus ay, y hat. Okay, so I could do this. Okay, my acceleration vector would then be equal to ax times x hat plus ay times y hat. In general, one of those values will be 0. Okay, and that'll make the problem a lot easier for us, thankfully. Okay, so here's my example. Okay, I have a 12 kilogram wagon is being pulled by a little boy pulling on the handle with a force of 42 newtons. Okay, same problem, and now let's calculate the acceleration of the wagon, assuming there's no friction. Okay, so because we know the wagon is being pulled along the ground, we know it's not going to accelerate upwards or downwards at all. So we can set my y acceleration, or ay, to 0. Notice also that I've had to define my positive directions just like I did with projectiles. In this case, up is positive and right is positive. So what I'm doing now is I'm adding up all the forces in the y direction, paying attention to which ones are positive and which ones are negative. So my normal force, okay, and I'm using the abbreviation here, okay, my normal force is this one, and it's going up, so it's positive, so here's my normal force. Okay, my force applied y, I'm not using force applied anymore, I'm just using the components, it's there. And there's my force applied y, also positive. Okay, and then last I have my force of gravity, okay, force of the earth on the wagon. And that's there, and because it's downwards, this force is going to be minus. And that is all going to be set equal to 0. Okay. On the x-axis, okay, I only have one force on my x-axis, and that's this one, okay, my force applied x. And that's going to equal my mass of the object times the acceleration in the x direction. Okay, using the substitution that we calculated before, okay, my force applied x is 42 times the cosine of 30, and then I have the mass of my object times the acceleration. So I end up with a total acceleration of 3.03 meters per second squared. Okay, so that's today's lesson. Thank you very much.